Okay, this is the third and final video on section 6.1. That's power series and functions. And here we're going to be representing functions as power series. So recall the geometric series where the common ratio in absolute value was less than 1. That was a plus ar plus ar squared plus dot dot dot. That is where it's going to converge, is when the absolute value of r is less than 1. That converged to a over 1 minus r, and then we wrote the series as the sum n equals 0 to infinity of ar to the n. So if we take the function f of x equals 1 over 1 minus x, this can be represented as a geometric series, provided that the absolute value of x is less than 1. So 1 over 1 minus x, the function, can be represented as a power series, sum n equals 0 to infinity of x to the n, again, provided that the absolute value of x is less than 1. Alright, so let's try this out. So, example number 12, let's find a geometric power series for the function 1 over x, and then we're going to center it at x equals 7. So 1 over x, we can rewrite this. So I want it centered at 7. So if it's going to be centered at 7, I need x minus 7. So what we're going to do is we're going to put an x minus 7. So there it is. There's your x minus 7 right here. And to offset that, we need to add 7 so that these are equivalent. So this becomes 1 over 7 plus x minus 7. So to get the form of a over 1 minus r, we're going to have to do a little bit of manipulation. So this is going to be equal to 1 over 7 minus negative x plus 7, okay? And so we can go ahead and check. This is 7 plus x minus 7, so that's still x in the denominator, so that's looking good. Okay, so we got this matched up. We need a 1 right there. So how we're going to get a 1 right there is we're going to divide everybody by 7. Okay. So 1 divided by 7 is 1/7. 7 divided by 7 is 1. Minus, and then the negative x plus 7 divided by 7. Okay, so now this fits the form of a over 1 minus r. Okay, so the sum, n equals 0 to infinity of ar to the n, is equal to a over 1 minus r. So we're taking this and we're going that way, where r in absolute value must be less than 1. So this is equal to the sum, n equals 0 to infinity of 1/7 negative x plus 7 all over 7 raised to the n power. So we want to rewrite this so it looks more like a power series. So this is going to be the sum, n equals 0 to infinity. We're going to factor out a negative 1, and then it's to the nth power, so negative 1 to the nth power. And then you have 7 to the n, and then also a 7, so 7 to the n times 7 is going to be 7 to the n plus 1. And when we factored out the negative 1 out of the negative x plus 7, that makes it x minus 7 to the n. And so now that looks like a power series. And we're going to find the radius of convergence. So this is a geometric series. Our common ratio is this right here. So it's going to converge when the absolute value of negative x plus 7 over 7 is less than 1. So multiply by 7 and then rewrite this. So this is equivalent to negative 7 is less than negative x plus 7, which is less than 7. Subtract 7 from all three sides, so negative 14 is less than negative x, which is less than 0. Divide by a negative 1, and that's going to reverse the inequalities. So 0 is less than x, which is less than 14. And so our interval of convergence is 0 to 14. And notice that that is centered at 7, and the radius here is 7. Okay. All right. We got 2 more examples. We're going to do another one of these, finding a geometric power series, and then we'll do just finding an interval and radius of convergence using the root test, since I don't think we've done any examples of the root test. All right. So this time our function f of x is going to be x to the ninth over 1 plus 5x to the ninth. And we want to write this as a over 1 minus r, so we can use the sum formula for a convergent geometric series. So we're going to go ahead and rewrite this as x to the ninth over 1 minus negative 5 x to the ninth. So it's going to be the sum n equals 0. Your a is going to be x to the ninth. Common ratio r is going to be the negative 5x to the ninth, and then that's raised to the nth power. So we can rewrite this as the sum n equals 0 to infinity, negative 1 to the n, 5 to the n, x to the 9n plus 9. And if we want to find where this thing converges, that's when the common ratio, which is the negative 5x to the 9th power, is less than 1. So negative 1 is less than 5x to the 9th, which is less than 1. Divide all three sides by 5, so negative 1/5 is less than x to the 9th, which is less than 5. And then we're going to take the 9th root. The 9th root function is an increasing function. And also the 9th root of negative 1 is negative 1. So we can slide the negative out. So this is going to be negative 9th root of 1/5 less than x less than the 9th root of 1/5. So that's going to be our interval of convergence, which is the negative 9th root of 1/5 to the positive 9th root of 1/5. And a radius of convergence is going to be 9th root of 1/5. Okay. All right, got one more example here, just an example of using the root test here for finding the interval and radius of convergence. Okay, so we're going to use the root test to find the interval and radius of convergence for this series here. The sum n equals 1 to infinity of 9n squared minus 1 divided by n squared plus 8, that whole thing to the nth power times x to the n. So we're going to look at using the root test. So the limit as n goes to infinity of the nth root of the absolute value of 9n minus 2 over n squared plus 8, that's raised to the nth power, and then times x to the n. So this becomes the limit as n goes to infinity. The nth root and the nth power will absorb. So we have 9n squared minus 1 over n squared plus 8. That's always going to be positive when n is greater than or equal to 1. And we just need the absolute value on the x. 9n squared minus 1 over n squared plus 8. You got to tie in degrees. So the horizontal asymptote is going to be the quotient of leading coefficients. So that limit's going to be 9 over 1, or just 9. 9, and then the absolute value of x. And for the root test, we want the nth root to be less than 1, and that's the limit of the nth root is less than 1. So divide by 9, and so we have the absolute value of x is less than, divide by 9. So this should be a 1/9. So let's go ahead and fix this here. So this is negative 1/9. Less than x, which is less than 1/9, and so then our interval of convergence is going to be negative 1/9 to 1/9, and our radius is going to be 1/9. So let me go ahead and fix that there. Alright, so that concludes our final video on section 6.1. Stay tuned for section 6.2. So 6.1 and 6.2 are going to be probably on the longer side. 6.3 I think is going to be a little bit shorter. So we'll see you next time.